Hello, everybody. I'm Marianna Parzych, and I'm a data scientist at deepsense.ai. Today, I want to talk to you about the transformation invariance of convolutional neural networks. CNNs are commonly assumed to be invariant to some small transformations, either because of the architecture or because they were trained using data augmentation. And today I will show you if they are really resistant to small shifts or rotations, and why should we worry about this. During the presentation, I will try to explain why transformation invariance of our models is important. Next, I will present an analysis on transformation invariance of convolutional neural networks. And then I will show you different methods for ensuring the geometric robustness. At the end of the presentation, you will find a list of references and implementations to try in your own projects. What is our motivation? Consider a state-of-art deep CNN. It generalizes well on some task the client needs, like classification or object detection. It was evaluated over validation and test set, obtained very good performance metrics. And it's used on production, performs with expected performance. So everything seems to be perfectly fine. However, we don't know if this network is immune to some minor transformations of the input image, like shifts, scales, or rotations. Before we continue, let's define the translation invariance. A fully translation invariant system will give the same output to any image and a translated version of this image. It means that whether the system sees the first, the second, or the third image, it will return the same response. We want our network to behave that way because no matter how image was shifted or rotated, it is still a photo of a person. So we don't know if our network that seems to be fine is translation invariant. But is it actually important, and should we worry about it? Let's consider what would happen in different scenarios if our model was not translation invariant. In case of quality control, same item tested a couple of times gives different results. Such a situation happened to me in my professional career. I was working on the quality control project, and one day client reported that during testing the same item, system returned different defect lists. No matter how good the metrics our model achieves, and no matter how well the system performs in general, if something like this happens, the model is perceived as unstable and unreliable, and especially for people who don't work with neural networks on daily basis. So the client was very concerned about it. In case of uncontrolled acquisition, changes in perspective and scale will give different results for the same object or scene. In case of video processing, we obtain different results for consecutive frames. This is also example from my experience. I was working on a video object detection project, and detected object appeared and disappeared through the film, even though frames looked almost the same. And I didn't understand the cause of this problem at the time. So a lot of work went into tracking and detection sustaining mechanisms. Well, then it seems not that fine anymore. And that's why I think it's worth addressing this issue. So are the CNNs transformation invariant? Actually, they are not. In the picture, we can see the test conducted on altered images. Images in the first row was classified as binoculars and shifted for 1, 2, and up to 8 pixels. Images in the second row was classified as warplane and rescaled by 1, 2, and up to 8 pixels. And images in the third row are consecutive frames from the video that shows an otter. The differences between these photos are practically imperceptible to human. However, the possibilities of the proper class differ a lot. In many cases, the probability of expected class is less than half, so most likely the highest probability was given to some other class and predicted label changed. Here we can see different type of test. It was performed on 100 randomly chosen images from ImageNet. Those images were perturbated in different ways. There were specific scenarios, but what is most important to interpret the results, difference between compared images is on order of 1 pixel. So it was 1 pixel shift or 1 pixel scale from 100 pixels to 101 pixels, etc. And the results shows that networks give different outputs for these images, although different image processing scenarios resulted in bigger on smaller mean change. The probability of change in top one prediction was never zero. This is very disappointing because convolutional neural networks should be, if not translation invariant, then at least translation equivariant. Translation equivariance is a feature of convolution. It was the first motivation to use convolutional layers for image analysis. For some of you, this might be obvious, but those who don't deal with images on the daily basis, you can see how convolution works in the image. For each pixel, the new value is computed based on the constant kernel and the values of neighboring pixels. So this means that if input image is translated, the output of the convolution is also translated, but the new value of each pixel is the same, just like in the image above. So, are the CNNs translation equivariant? Sadly, they are not. You can see it on the image. It shows feature maps computed on images that were shifted imperceptibly. And feature maps differ. And the differences are the greater, the more layers of the image has gone through. Now I will try to explain why is this happening to us. Before we go any further, we need to briefly introduce some definitions from signal theory. First is sampling. In signal processing, sampling is the reduction of continuous time signal to sampled, discrete time signal. A continuous signal has a known value at every moment of time, and a discrete signal has known values only on the sample moments. A common example of the conversion is an analog sound wave to sequence of samples, so to digital sound. And the sampling frequency determines how many samples in a given time or space we will take. Back to images. Digital images are already sampled, since the world we are looking at is not made from little squares. During the acquisition of digital photo, image is sampled and every pixel of our image is a sample. Historically, convolutional networks used convolution with stride equal to 1. This is something referred to as non-strided convolution, although this is incorrect because the stride is 1. Stride is the distance between spatial location where the convolutional kernel is applied. Like in this first image, we compute the value of the red pixel here, then we move our kernel by 1 pixel and compute next value. And the result of this operation has almost the same size as original image. We only lose this border due to the size of the kernel. But in modern networks, we usually use stride larger than 1. And it's usually called as strided convolution. And if stride is larger than 1, image is downsampled. Just like you can see it here. We compute the red pixel, then we move 2 pixels, compute the green and the blue, and our output is much smaller than the input. It means that frequency of sampling is now lower than before downsampling. And stride works the same for pooling layers. Here is the example of pooling with stride 2. Why is it important? To answer this question, we need to go back to signal processing for the moment and talk about sampling theorem and aliasing. Sampling theorem, also called Nyquist-Shannon criterion, says that the sampling frequency should be at least twice as high as the largest component of the processed signal. If the signal sampling frequency is too low, we won't be able to reproduce the original signal. You can see it on the image. There are not enough samples to determine which of presented signals was the input. The signals alias each other, and it's a problem of aliasing. This phenomenon is commonly illustrated in movies. So when you can see the car and its wheels appear to spin backwards, it's due to the frame rate not meeting the sampling criterion. And same thing happens when we use strided convolution. Sampling frequency is too low, and we lose information that can't be restored. But there is one more thing to about. Data augmentation is used during training convolutional neural networks, and any input image can be seen by network at different shifts, rescaling, rotations, crops. So we would expect that the CNN will learn to be invariant to translating the image. One possible answer to this is that networks only learns to be invariant to translation of the training images. And there is nothing in the training laws to make it learn invariance to translation of any input image. Analysis of the data sets allow to define typical and atypical images of different classes. Like here we have a typical Weimaraner and atypical examples. So intuition is that the network will be robust to transformation of images similar to those typical ones, but not to atypical images. Here presented tests show that CNN sensitivity to 1 pixel perturbations depends on how typical the images are. Plots show that sensitivity of a function plots shows 2 measures of sensitivity as a function of typicality for 1,000 randomly chosen center cropped images. And both measures of sensitivity depend strongly on the typicality of the image. So more atypical image was, it was more sensitive, the network was more sensitive to its transformations. Now we know that the problem exists and we know what causes it. So we can talk about how to address it. We can classify the methods into 4 families. First is reducing subsampling. If we get rid of subsampling, the convolution architecture guarantees translation invariance. However, it comes with a large computational price, and it's possible only for small images. Another thing we can do is increase data augmentation. It can improve the network's translation invariance. However, the problem will not be fully solved. Third family is anti-aliasing. These are methods that are based on signal processing theory. Anti-aliasing is low-pass filtering before downsampling, and this should make network translation invariant, but can degrade its general performance. And last type of methods is based on special downsampling techniques. First method I will talk about is based on increased data augmentation. Authors of the paper propose manifold, the algorithm for finding small worst-case transformations. I will not dig into mathematical details. You can find it in the paper or look at the implementation. But the main idea is to try different predefined transformations until we find the smallest transformation that causes the network to change its answer. And this transformation is then used as augmentation during training. And authors compared ResNet 18 fine-tuned with manifold with ResNet 18 fine-tuned with random augmentation, and manifold trained network achieves lower misclassification rate for transformed images. Authors of other increased data augmentation technique proposed two types of augmentation. Random rotations and translations from the ATEX space. It was up to 30 degree and 10% of pixel shift, or bigger attack space was 40 degrees and 13% of pixel shift. And then they proposed worst of K translation. So on each training step, random translations are performed, but the one on which model performed worst is used as training augmentation. They also propose vote-based inference procedure, compute a number of random transformation of the input image, and output the label that got the most votes. Networks trained with proposed procedure and evaluated with standard and vote inference were tested on the dataset altered with natural random perturbations and worst perturbations found with the grid search. And worst of 10 augmentation procedure performs well on this perturbated images, worstly perturbated images. Another way of ensuring translation invariance is anti-aliasing. As I already said, anti-aliasing is achieved by low-pass filtering before downsampling. But how to use a low-pass filter on an image? Frequency in an image is a rate of change in space. So a low frequency image may be one that is relatively uniform in brightness and changes very slowly, like this left image. And the high frequency image is a lot of change, intensity of an image changes quickly from pixel to the next. Low pass filter is a filter that passes signals with low frequencies and stops signals with high frequencies. So what is this low pass filter that would pass the left image and stop the right image? Well, it's simple blurring. And here we have an example of anti-alias layers. Authors of the paper propose to replace downsampling layers like convolutions and pooling with free operations, then evaluating the operator densely with stride 1, then perform blurring, and then naive subsampling with chosen stride. And here are the outputs of conventional and anti-alias network. And it is clearly seen that the stability of the results for different shifts is much better than in case of the black and is much better for the anti-alias network that is blue than conventional black results. And on this graph, we can see that, as expected, the anti-alias networks have a higher consistency of the results for transformed images. My intuition was that the use of blurring can make general classification actually worse. Surprisingly, authors claims that classification accuracy is also improved. And the last family of methods for ensuring geometric robustness is using special downsampling techniques. Here we have an example. Authors of the paper proposed a simple subsampling scheme. In conventional linear subsampling, we just choose samples depending on what is this layer, convolution or pooling. And if the image is shifted, our samples differ, like you can see it here. And in proposed subsampling scheme, we choose a set of samples, the actual ones and the shifted samples, and then select the one with highest norm component. And this approach assures that layer will give the same output for original image and for slightly shifted image. Once again, I won't dig into math since I am not a mathematician, and you will gain more by studying the article with proper focus and at your own pace. Take your time. Here is a table that shows that proposed subsampling techniques allows for better consistency in comparison to baseline models, but also in comparison with anti-aliased networks, LPF here. Authors of the next paper propose another subsampling technique, and they claim that their technique is a generalization of the APS we talked before and allows for better accuracy while consistency is still 100%. And authors, in addition to downsampling technique, propose upsampling that can be used in encoder-decoder architectures like in segmentation. To sum up, we know that modern convolutional networks are not translation invariant nor translation equivariant by default. And the reason for this is the use of downsampling, strides in convolutions and pooling. It is a good idea to evaluate the model for the resistance to small geometric transformations. You can use the vote inference for every network. So run the inference on the set of random transformations, slightly transformations of the input, and use the most frequent answer. To train anti-transformation invariant network, you can use one of the different methods like increased data augmentation, anti-aliasing, and special downsampling techniques. I would personally start with trying downsampling techniques since they are the newest and claim to have the best accuracy on benchmark datasets. I will now show you the references. You can find on the end all the references, sources I used to prepare this theoretical explanation, but also papers presenting methods and that can be used and their implementations. So we can find here the papers about increased data augmentation. Here you can find papers about anti-aliasing. I only presented one of them, the first one, because they were very similar to each other. But if you're interested, you can check more papers and different implementations. And here you can find paper and code for APS and LPS sampling. And that's all. that's the end of my deep talk. I hope you enjoyed it, and maybe we'll use some of those presented techniques in your computer vision projects. Thank you for the participation, and bye.